All right, we're back with our 11th edition of the podcast with Eliot. And you and I spoke about this before. I wanted you to come on because you have a lot to say, and I hate that half of our conversations on the phone aren't recorded anyway, which is we should probably just start FaceTiming and recording them.
Oh, you can
But
just hit a button on your iPhone now. Eddie does it all the time. His
really,
cheek hits the button. Yeah, his cheek hits the button by mistake and he starts cursing.
then the whole thing's recorded. But there's something I've been thinking a lot about, which I have a feeling you'll have something to say regarding. I want to keep this focused around air and water performance, although we're probably going to end up focusing on the thermal side of things. But the theme of this podcast, I think, should be how we have some of these industry standards around AMA test sizes and NFRC test sizes, and how you create some type of infrastructure to allow AMA gateway sizes. So you create something where you create some test criteria that allows you to compare a handful of manufacturers across the industry that are either scrutinized under the same criteria as a means of comparing multiple different products for the end user to be able to easily digest what is it that I'm paying for, and am I buying a premium product on paper in lab conditions?
Or a qualified product.
Right. What gets confusing to me is that that's all well and good, but how often are those modeled products, conditions, or tested products or conditions actually what ends up getting installed in the field? And what is the real impact then on your as-built condition? In terms of, two things, we could talk about the energy side, but more so how the assembly in its entirety should perform. Um, and are you comparing it to your lab results, or are you making concessions in terms of what the expectations should be in the field? To start, maybe you can give a little bit of these infrastructure some grace and explain how there are limitations here, and acknowledging or appreciating site conditions is not as simple or easy as one might allude to on a podcast.
Sure. So I guess maybe we back up a step or two here. We refer to it all the time as AMA gateway sizes and AMA testing, but really for the last 10, 15 years, it's been NAFS, the North American Fenestration Standard, which is a harmonized standard in the US and Canada, although it's used by other countries to give us a rating system for windows. So ratings are overall suitability guidelines, right? They're not engineering, although a lot of people use them as engineering. And even the NAF standard kind of indicates that as long as the window is under the test size and it's installed in a similar way, you should be able to not do job specific engineering and job specific testing. But it doesn't come out and literally say that, right? They're just giving you a means of judging suitability of a product for a project. And it's a very good method of judging suitability of a product, right? It gives window grades, residential, commercial, architectural, and then it gives performance, which is the number after the letter. When you see an AMA test report or a NAFS test report and a window rating, right? It's also to give people confidence that the manufacturer, when the product is certified and labeled, not just a test report from Eliot's lab, but a listed and labeled product, gives the consumer, the specifier, confidence that the window is going to perform that way every time. Now, whether or not that actually happens in real life, probably not. But at least if someone's gone through a certification program, whether it's from FGIA AMA or CSA in Canada or the Window and Door Manufacturers Association, you can have confidence that that manufacturer is more serious and is doing more quality assurance, quality control, because there's more risk for them to lose their certification on their product if it turns out that they're not doing proper quality control. How does it relate to the installed product? So it does and doesn't. Obviously, you can use the labeling or rating system to determine, is this window suitable for a school, or is it only suitable for a low-rise office building or a high-rise residential multifamily building that's over 75 feet? 75 feet an important cutoff for most people, and you'll see it showing up in lots of areas in the building code. I don't know where exactly it came from. Someone once told me that's as high as fire truck ladders. Actually, it was Ian who told me this. He said the 75 feet came from the highest fire truck ladder could go. He said that's where it originally came from. And that became like a standard that we use for how we judge whether or not a window or any other product that is installed is going to be suitable. It's that 75 foot or 90 foot cutoff. 90 foot, I think, is more from ASCE calculations, but a lot of people still use 75. So lots of people say if the building's less than 75 feet tall and I'm buying a rated certified product and I'm installing it per the manufacturer's directions, it's going to be fine. Maybe, maybe not, right? The manufacturer has a limited amount of pages on their website and pieces of paper they can publish, installation instructions, and it doesn't always match the conditions on the site. So it's a good starting point. However, the architect or the engineer, or sometimes it's the window installation company, should really look at the details and say, hey, we want to look at this because we're not sure the detail that's shown on the drawing is going to work and still give you the performance you're expecting from the windows we're going to install. You move the caulk joint all the way to the back of the window frame. You have a rain screen system. We're afraid that water's going to sit on the head of that window, even though it's a rain screen and technically it should all drain away. A window is not built to drain water out of the head profile of the window usually. So water's going to sit in that window head, maybe compromise the corner seals when they assemble it, and all of a sudden over time you're going to get a leak. It's the same thing with structure, right? When we test windows for certification in the lab, we install it in a wood buck, which is basically dimensional lumber 2x10. We use 2x10 lumber frame that we build and install the window into. Now, there's no guideline in any of these certification programs about how you should install that window in the buck. Some people do it with buck holes through the frame. Some people do it with moldings on the inside and out, slide-in anchors, twist-in anchors, you name it. We've tested it all different ways because there really isn't a specific guideline for how it should be installed in the buck. So if you want your window to perform better, just put a screw in it and through the frame every 4 inches. Structurally, it'll work great. Water, it may or may not, but when you're in the lab, you have all the time in the world to seal off every hole. When we get out in the field, if we use that as the guide for how to do the installation and you put 20 holes in that frame, it's not a very good detail for water and air penetration. So obviously what you're saying about the installed or in situ details compared to the lab tested details are almost always, if not 99% of the time, different than what you did when you were in the lab. And the test reports don't necessarily tell you how the window is installed into the test box. So it gets very, very complicated. And I think we have to have more industry education for people. Absolutely. I think that's critical. That's why this podcast is so instrumental in getting people asking questions, right? That's the first step. You're asking a question that people are now going to look at their project and say, hey, what are we doing for this window installation? Are we looking at this? Are we looking at that? Are we looking at the installation details? Or are we just getting a line through something, a piece of wood or a piece of aluminum, showing a line through it that's supposed to indicate a fastener or an anchor? And that's a real important question to start asking. And there are experts out there. Most of the domestic and some of the better overseas manufacturers have application engineers on staff. Application engineers are your first call when you're unsure about something. Call the window company that they're either proposing or they're using for the project. Say, can I speak to an applications engineer? I have an installation question. They're really knowledgeable people, and they're going to look at your detail and say, hey, we would prefer if you did this. We're more comfortable with you doing that. And they will do quite a bit of free engineering for you for your project. And lots of times they provide you quick detail. They're not going to do a whole package for the job, but they're going to give you a good head, jam, and sill detail usually for free. You didn't have to hire a consultant. They're there. And their motivation to get it right is they own the warranty. They don't want to see you installing it wrong. So take advantage of that resource that's out there at all the traditional companies that are around, whether it's Anderson Windows or EFCO or Warsaw. They all have some resource internally for that. Some have more than others, but you can eventually get the help you need if you ask early enough. Then there are the facade consultants, right? You and I both worked for a big one in New York City at one time. I was a long time before you, but you have consulting engineers that specialize in facades, and the deliverable that you're expecting out of them could be, I need you to review these details for me and make recommendations, or it could be, I need you to get very involved with this project because it's very, very complicated. We're trying to do something that we never did before. Can we get you on board and have the owner retain you to both help us design the project, review the shop drawings, inspect, go to a mock-up if we're going to do a mock-up, and so on. And those are good resources to look at the custom side of these jobs. And almost every job's custom, unless you have a home builder who builds the exact same 6-inch stud wall with gypsum exterior sheathing. You always uses the same air barrier, always installs a certain way. And there are builders, especially on low-rise construction, that do that. And they've worked out their detail and they know it works. So limited risk there. But when you get to more complex high-rise buildings, complicated low-rise buildings like museums and hospitals that have really unique or important conditions that need to be met, those jobs usually need some expertise involved with it. You can't just think that we're going to figure it out during shops. It's not going to happen.
You figure it out during construction.
Or during construction.
Do you think manufacturers are doing themselves a disservice by issuing publicly or not, or to project teams, test reports that might go above and beyond what might be required for 95% of the work that they participate in? If a manufacturer publishes a test report that their fenestration system can, meet 15 pounds of water pressure, water penetration resistance, and 90+% of the work that they aren't participating on doesn't require that, all of a sudden an architect incorporates that performance criteria into their project specifications, and a manufacturer bids the job and is awarded the job that can't comply with that criteria. The architect's going to communicate to the owner that they're buying a lesser product or a less premium or lower performing product. And you get into this mess of saying, well, the specifications say 15 PSF. Why can't you abide by it? Why didn't you make that clear during the bidding process? And I think the question, you said it's about asking better questions. It's asking the question of, why did you specify that fenestration system? Did you intentionally require that water penetration resistance? Why? What are the design pressures? What is the water exposure? What is the wind load exposure? What are going to be your requirements in the field?
So again, this gets back to industry educating the specifiers and the end users. So the test report, or even a certified test report and a label, is only your ticket to get into the game. It doesn't mean you're going to win. It's your ability to get qualified to bid the job. And we shouldn't look at these test reports and say, oh, it's a 15 PSF window. It's going to perform at that level on everywhere on my building. Is your building even in a zone that needs to resist a 72-mile-an-hour wind-driven rain? I mentioned grade and rating, right? So we have a performance grade, that's the C, A, W, R. That tells you the appropriate use of that window. It's a residential window. It should be in residential buildings. By residential, I mean low-rise, single-family or small multifamily buildings up to 6 stories, let's say. Commercial is a commercial building. A larger building maybe has more specific usage, has to resist a higher wind load, things like that. So the grades are there. The number that's after the grade tells you the wind load it was tested to. So when we say a structural design pressure, we're referring to the equivalent static pressure of a wind load. So if the wind blows at 50 miles per hour and hits a flat surface like a window or a wall, there's an equivalent pressure that wind pushes against the wall with, or pulls against the wall with, if it's on the leeward side of the building. We convert that wind load into a pressure. In the United States, we use pounds per square foot. Everywhere else in the world uses pascals. It's honestly a pain in the ass to work in PSF because we then have to convert PSF into inches of water. So people always come to a test and ask us, when is that gauge going to hit 10? And we have to explain that it's never going to hit 10. The equivalent static pressure is 1.9 inches of water. If we did everything in pascals, we wouldn't have to do any of that. So the Canadians are way ahead of us as usual on that one. But the important thing to understand is how these ratings and the water test pressure and the air leakage relates to the structure. So the wind load is the first thing people are supposed to look at. My building's in a city that's not on a coast. It doesn't really get high wind exposures. You know, the building code says it's a 25 mile per hour base wind speed for the building. You do your calculations based on ASCE 7, and you come up with the maximum wind load at the corners and the roof and all the different zones of the building is 22 PSF. 22 PSF design pressure is equivalent to either the appropriate water test pressure is either 15% of that 22 or 20%. So 20% applies to architectural grade windows, 15% of the 22 PSF applies to everything else. It's a low number. What's 15% of 22, right? It's under 4. And we still see architects wanting a very high water test pressure because they think that protects them from leaks in the future. Believe me when I tell you, Adrian, very few failures we see are from the system getting overwhelmed by the actual wind-driven rain. 90% of the leaks we see are workmanship or design. So either we're interfacing with the other products on the building, that air barrier, that whatever it is, that block, it's the interface, or within the construction of the system, whether it's a defect at the window, someone ripped the gasket, they didn't do a corner seal correctly, they didn't tighten a screw, they didn't do something. That's a defect that was usually happens in the factory, or when you're assembling windows into an opening, whether it's a residential wood double hung window that gets molded together with a fixed window to create what we call a picture window setup, which is double hung, fixed double hung, or a high rise window wall that's getting molded as you go down the wall and interfacing with a receptor system, whether that's installed incorrectly. Most of the water leaks and air leaks we see are from defects, not because the system was overwhelmed. It was overwhelmed because it's leaking air usually. So if a sill on a window, water comes in over the sill, and we're at the test pressure that the system was designed and rated to, it's not happening because the system, they're lying to you about their sill capability to resist water pressure. It's happening because you have an air leak on the wrong side of the window that you don't see, and it's causing a straw effect. It's sucking the water up beyond where it's supposed to go if you had true pressure equalization in the system, because somebody didn't seal something correctly, or a designer insisted on having a detail that the manufacturer doesn't use for a reason. And now all of a sudden you're overwhelming the system because you allowed the air to get in and defeat your pressure equalization design. That happens more often than not. So just picking a 15 PSF water resistance rating doesn't guarantee you that you're getting 15 PSF. And it may not even be appropriate for the building because you may never see that kind of wind-driven rain. You may never see a 72 mile an hour wind-driven rain at that building. Now, does an architect or an owner have the right to say, I still want the high test pressure for the water? Sure. But you have to realize that that will also drive up the rest of the window cost, because that window grade and rating now is much higher. So you may have a 3-story office building with little exposure, but I want it to be water resistant. The manufacturer looks at it and says a 15-pound window is based on this structural rating. And now instead of using maybe a 3¼ inch frame window, I have to go to a 4½ inch frame window with all that more framing, heavier glass, everything else. So understand where the water test pressure is important and where it comes from. It comes from that wind load. Initially, that's the 15 to 20% of the wind load or the design pressure. A very, very good resource. You mentioned AMA before. So AMA is now called the Flat Glass Industry Association, or FGIA. 40 years ago, they wrote this document called the Window Selection Guide. It hasn't really been updated, but honestly, the information that's in it is invaluable to architects, engineers, facade consultants, estimators in window companies. It's the Window 101 document that not 101, but you know what I mean, the Windows for Dummies book that everyone should pick up, should go and buy. I wish they gave it out for free. I've argued this at AMA for years. This and the curtain wall guide should really be free documents, because we don't have the resources to go out and educate people one-on-one or even lunch and learns in groups the way we used to. But this document, it's very dry reading, but if people can actually sit there and really digest it, read it a few times, you will know enough about windows to feel confident and do a good job of getting windows specified, reviewing submissions. It is really a critical document for everyone listening to this podcast to read. And so is the curtain wall guide.
That example you used before, where the developers building the 4 or 5 story building with low exposure, maybe 20 to 25 pounds of pressure, do you think they are better off spending more money to go on the deeper system with heavier wall sections, or go with the shallow, thin wall section frame assembly, but spend more money on testing in the field during construction? Because if you're going to have these leaks, they're going to appear, in the first month or two post installation.
So obviously, we don't say testing. We say quality control, because testing is one part of a good project, right? What we do is we like to get one of the first few windows installed, run a field test on it, and find out if there's any problems, things we didn't see on paper or on a screen these days, and then identify a problem, which we do. And then what do we do with that? I come to the job 3 times, 6 months apart. I'm not there checking on every window. An inspector is there checking on every window, who will use the report we give them and the information that we found or the defects that we found to say, I'm going to check this in the factory and I'm going to check this as they install. And we're going to make sure that those problems, because just because the window fails the test you shouldn't be holding that as a fail for the job. It's information. It's useful information that inspectors, whether it's a third-party inspector, which is required by code in almost everywhere in this country now, or it's a general contractor, which there are very, very good general contractors now who are conscious of their risk and hire young people who are recent graduates from architecture and engineering, and they call them project engineers, to go around and be responsible to make sure that things are being installed correctly, coming to the job site correctly. Our testing only supports that.
But the only one you didn't include is, what about, I've worked with them, and you were on this job, you've worked with them too. What about the curtain wall contractors that are doing their own flood testing, that are doing their own chamber testing before the owner's, testing agency comes on site?
I love that. I like contractors and manufacturers who take the initiative to check their work. Flood testing, hose testing. It's simple, cheap. Lots of people hate it. Lots of people say it's not a test. Okay, it's a quality control procedure. There's nothing I do that's more important than quality control. I have fancy equipment. We build these crazy chambers. People see us hanging racks from 40 stories up. It all looks cool. You know what? Flood testing sills, putting a poker at the caulk joints to make sure it's not separating away from the substrate. All these simple, cheap, inspection, quality control measures are as important as anything we do. Sorry if you hear that. That's the guy starting up a dynamic fan in the shop. They're working on a carburetor.
Well, right. So
Yes,
yeah,
I like the manufacturers to do their own testing. I like the installers to test their own work. And I just think that they shouldn't be penalized for that, which we see lots of third-party inspection companies. It's like a suspect act. It's like they're cheating. Don't look at it that way. Just tell them, listen, we want to know what you're doing. We want to know when you're doing it. We'd like to come around. And if you could please send us a report and don't hide the fails. Tell us when you have the fails. We want to know what to look for as we go. We believe you that you're going to fix it as you go. We'd also like to have second set of eyes on it and document that you did have a problem, fix the problem. What can an owner want more than a responsible contractor manufacturer that knows they're not perfect, because no one is, and goes back and makes it right by testing it and fixing it? And most of them do it. Most of them want to do it, but the industry is a little twisted to thinking that that's a bad thing. It's a good thing. Let them flood test, let them spray test, let them do everything. We'll come and do the official test. If they get it right, don't tell them where we're going. Just make sure that we're in the range of stuff that they did, whatever remediations they have to do, and then we come and do the official test.
I would say for any large scale commercial fenestration supplier, curtain wall, window, you're going to see them doing in-house testing regardless while they're starting up production or throughout production. Why wouldn't you expect them to be doing that in the field? And part of it is work out the kinks in the shop before it gets to site. But has to be a little bit more of a mentality. Work out the kinks 5 to 10% of the way up rather than 85 to 95% of the way up.
Absolutely. We're schedule oriented, and we should be more risk averse than schedule oriented. And again, in some places they are. The Midwest, Arizona, Montana, the builders who are big in the rest, so that the coasts are a little different. LA's, I think, a little better on quality control than we are, but then you get to other places where they're worse. But yes, the schedule dictates everything right now, even though interest rates are relatively low. I'm an old man. I remember when builders or developers borrowed money at 13% to build buildings. For the last 10 years, they've been borrowing it for nothing, basically. What does an extra few weeks or a month or two cost you to do a schedule that's going to protect your bottom line? So Eliot's guys don't have to come to your building to do a leak investigation, peel back the sheetrock, and say, I'm sorry to tell you this, but that wall has to come down. You have to empty out all these apartments in your building because there's black mold, and that OSB is a pile of dust on the slab, and you're structurally compromised, not just water. Now your walls are structurally compromised. And I'm not making this up. We get 2 or 3 of these a year where we have to be the bearer of bad news. And you don't want to be there. You don't want mold. You don't want leaks. You don't want compromised walls. You want buildings that you invested lots and lots of money in, whether you're building in a holding, building in a flipping, someone's owning that building as an asset, whether it's 50 shareholders in the building or an institutional real estate company. That building is an asset. You have to treat it like it's a long-term asset. You don't want it to cost you money in 10 years. You want it making money for you in 10 years. That only happens when the elevators work right, the boilers work right, the lighting works right, and the facade works right. Because if the facade doesn't work right, it's going to cost you money every year. You're going to lose tenants. You're going to have low occupancy rates in that hotel. You're going to have spaces that are not comfortable to work in during different times of the years. All these things cost real estate companies money. It's just very hard to track until it's a disaster.
From an air and water standpoint, it's somewhat challenging to model these things, but now looking at structural and thermal, because you look at many reports and simulated models and fancy this or that somebody spits out from some software, and then you actually do the real testing in your shop or on site. When it comes to structural or thermal, where have you been more surprised in terms of what can outperform a model in terms of real life conditions? Have you found that systems can really be pushed structurally far more than a set of calculations will determine, or can these systems actually perform better thermally than we once anticipated?
So we get both, and we get it both ways. So structurally, people have been conservative over the years with traditional curtain wall mullions and traditional window systems, especially pre-polyamide dog bone European thermal breaks, right? When we were using poured into bridge and aluminum windows, and I'm gonna talk about aluminum more than vinyl and wood, because vinyl and wood, the structural stuff is not as, I don't want to say important, but we don't get the challenges that we get with aluminum window systems. So for years, the windows performed in the lab better than they showed in calcs, because engineers are conservative. They use safety factors. I test in the lab. I'm not really using a safety factor. I'm told to hit this pressure. I hit the pressure. I measure the deflection. That's it. I don't do finite element analysis. We're measuring the worst deflection point at a specified pressure. So for years and years, they did well in the labs. We had no problems. Then we started building windows to modern energy codes that are 50% aluminum and 50% plastic. Good plastic. I hope Helen doesn't yell at me about this, but very good plastic, but still plastic. And the plastic reacts differently at different pressures, temperatures, everything. It's plastic. And there's plastic reactions and there's elastic reactions, right? And we have to know the limits of those things. Plus, we have to, again, educate engineers that this is not a piece of aluminum. It's a composite of two pieces of aluminum with a plastic separation that has to be looked at that way. And again, I'm going to go back to AMA. There's a technical interpretation. AMA calls them TIRs. It's an industry resource, not an interpretation. Sorry. There's a TIR for how to handle thermal breaks or thermally broken aluminum profiles and how to derate the system's ability to resist deflection and buckling, right? We have formulas. They've been proven out over the years. Committee's active right now that manages that stuff and that does it. Some of the smartest guys in the industry are on that committee. They do some of the most complicated work, which, by the way, they prove out with physical testing. We do round robin tests. We take some mullions from Cornier with a thermal break. We get 50 of them and they ship them to different labs who do the same test at different facilities to see if we get consistent results. So it's well studied and totally unknown in our industry. This is a document, again, needs to be given out for free because it hurts us when someone makes assumptions about a profile and then we get it in the lab and they fail structural by a lot. And then we have to explain why in AutoCAD they made this a single region and just treated it as if it was all aluminum, because there's a lot of data out there that says, oh, they have the same I value, they have the same thermal coefficients. That may all be true at certain conditions, at others they're not. And we really do need to educate the industry about how to make that happen. Thermal, I could talk all day about why we shouldn't be using a thermal rating system for windows and fenestration to judge energy calculations. U values, which are really U factors, NFRC numbers are not U values, they are U factor ratings. It's a rating so that Adrian can go into Home Depot, walk down aisle 28 where the windows are. He looks at a window A on the left that has a 0.40, window B has a 0.40 on the right, and he knows those two windows should perform about the same. One's twice the price, and if the thermal is more important to him than the colors or the handles, then Adrian's going to pick the cheaper one, and he feels confident it won't perform thermally worse than the one with the gold handles. That's what NFRC ratings were meant for, not for sticking into a whole building energy model and using it to calculate energy loss and gain through the envelope. Somehow that became the standard of how we do things. And it's why we can't achieve the LEED results, the passive house, all these results that we predict by doing all this modeling in advance of building the building. And we build the building and it's performing 30 to 50% worse than a model. I am not against ratings of windows. We need that to be able to build consistent buildings that are good. That's not the same as analyzing energy loss through an envelope.
So before we before we go down this rabbit hole, I'm actually gonna turn it to you. Do you want, because we're going to end on these two topics, do you want me to press you on the structural or the thermal side?
Either one. The thermal's more relevant right now. I think structural.
This is on the structural side. I think both are relevant. It depends on what capacity. What you just said about aluminum limitations and the thermal coefficient of the materials and how they'll behave in time under different conditions. I don't know why my head went to, southern Florida, where you see these crazy spans, under incredible wind loads. But now that you think about it, it's just because it's a hollow aluminum section. So of course it's going to work well. But
it's well understood. Just like steel shapes, an I-beam, a W member, we know exactly how to design with that. It's
fine. So if you look at a thermally broken aluminum profile, two sections of aluminum, and let's say a huge thermal break. So maybe you have more plastic than aluminum. So it's a composite material. Your skin or your shell is aluminum. The core or the backbone or the structure is plastic, the good plastic, but plastic. Let's put that in reverse and look at a commercial grade UPVC window. Now you have the plastic as the shell and, let's say, steel as the structure or bone. You just said we understand how steel sections behave. That assembly is also a composite. So is the problem that we haven't done enough testing and there's not enough case studies of this type of assembly in an application where you're exposed to higher design pressures and wind loads, and that's the concern?
It's the higher wind loads and the very, very large sizes that we're starting to see. People are using very, very good German designed UPVC windows as window wall. Same thing with fiberglass. We see fiberglass guys, not necessarily with steel reinforcing, but using it. So beam theory, you're a PE, how do you evaluate a beam? Simple beam calculation is between two fixed points, right? How's that steel reinforcing fixed? How is it transferring shear? How is it doing all these things? We put it in because we know practically it makes the vinyl section stronger. In theory, or when you're really doing higher level than just deflection, and what are your assumptions when you do that deflection calculation, right? Are you considering it fixed? Is it a moving joint? Is it everything has its human input. Whatever software you use has its human input, which is where I get worried, right? Again, we need more guidelines. We need more industry analysis, industry study of how these things are being applied to the windows in the way it's manufactured and the way it's installed. And we need guidelines for how to evaluate that structurally.
So how are the sections pieced together if
the steel slid in? The steel
I know you can handle my probing. So it's slid in. So how are the two vinyl extrusions, how are they married together? How are they crimped together? The steel is slid into the sections before you then weld the corners together?
Yes. So it's not technically continuous. It's truly reinforcing. It's not acting as a composite because you're not making a stress transfer. So the vinyl
so you have separation between your steel sections.
I mean, if it's only slid in and it's not tight or it's not screwed into the vinyl and a lot of screws to make, a shear transfer needs a lot of freaking screws or bolts. It's that we're not doing that most of the time. I've seen people do it, trying to do it, but you only have access usually to one side or the other. And plus, every time you make a hole in a window frame, you're leaving yourself open for window leaks. So people don't like to do that. So it has value. It improves your deflection. I don't think conventional calculations are the right way to show whether or not it's working. You know, we're at the point now where there's enough German influence on the fabricators in all parts of the world that are fabricating these very, very high-end Rayhow, Komerling, Galen windows, really beautiful, high-performance windows. And I think the fabricators are still relying on what the manufacturers of the system manufacturers are telling them to do. And they still go back to them, and they're conservative enough to protect them. But we're seeing people starting to say, oh, it worked on that. It should be okay on this, even though it's 3 foot taller, and I have horizontal mullions in the system, and I have this and I have that. And even anchorage, we've had fails in the shop. If you're putting reinforcing in a mullion, you need to at least have some anchorage at the end points of that mullion, correct? If you have any case for saying that this is really acting as a beam instead of just localized reinforcing, you have to fix the ends of those beams, correct?
Yeah, but isn't the fastener frequency or spacing like so intermittent in these traditional systems?
It is, but it doesn't matter because again, it becomes you have to look at whether you're analyzing this as a tributary, as a trapezoidal load, or a simple beam load, and what the tributary area you're assuming. Again, the human input, you can put it into whatever software you want to use, but how you are assuming this thing is going to react or what the assumptions are makes a huge difference. And I don't know if those horizontal sills on a vinyl window, whether or not they put steel in them. I think a lot of them do, but not all of them. And is it really going to transfer that load at that joint correctly? Those vinyl welds are nice and strong for the use of a window, right? Is it enough to transfer the load so that you could say, I'm going to assume it's trapezoidal here? Or is the majority of the load being taken by that vertical mullion? And I think most people today are more comfortable to say, I'm going to do a simple beam here, and I'm going to be very conservative because it's a plastic window. I'm putting it in a 35-story building, and I don't want to take any chances.
Can an argument be made that a welded connection can be more durable than a crimped connection?
Sure, it can be made, but it's not. We're welding plastic. It's good.
So that we don't know. In short, we don't know through enough experience and on the calculation or modeled side. So why isn't the industry doing more testing to prove some of this out?
Again, I think that the systems providers, the Schukos, the Rayhouse, those people are starting to say our systems are being used beyond what we predicted they would be used for. And I think they're starting to do that. But the industry evolves quicker than we can keep up with it. I said before, 15 years ago, Insulbar or polyamide thermal brakes were the same size as the port in the bridge thermal brakes, right? It was something that allowed aluminum guys to split finish so they could use one color in, one color out. Everyone wanted Insulbar because port in the bridge polyurethane was so bad, which it wasn't. But, that's where we started. It rapidly grew to 34 millimeter bars separating the aluminum now. And have we done that much research on all the different conditions that window sees, how it's being done? Are we getting enough education of the engineering departments in the window companies from the engineering departments at the Insulbar or the polyamide manufacturers? I don't know. Maybe we are. I'm out of that loop these days. Honestly, I'm also out of the loop on what's going on from the window system designer to the window manufacturers to the architect. I'm not as in the know on that end of it. I just see what we see. And what we see, I don't even see calculations on jobs now. 30-story buildings, no calculations, all one thing's evaluated for the calculation. The bending of the twist and anchor is evaluated. Everything else is assumed okay because the manufacturer says it's okay. That can't stand. We have done a total 180 in the last 5 years on this, where I know that I used to have to do an engineer. I used to have to support the crimped connection with engineering, right? Or the screws in the screw ports. We used to have to, which there are guidelines from the industry, from AMA, on how you should evaluate a screw in an extruded screw port and an extrusions. There isn't that level of detailed analysis and guidelines yet for what we're doing now, whether it's the stretch thermal breaks or the vinyl.
Right. So there's a resource issue, there's a maybe time constraint, and now I'm going to transition lastly to something you do know a lot about with the thermal side of things. I think my big
maybe
gripe,
we shouldn't.
well, I think this is important. I think my gripe is I understand the importance of having a rated system and understanding what U factor of an assembly is versus a U value of individual components. I've heard not only you say that on 10 podcasts, but now I see other people, and Gary, speaking about it on stage at conferences. So I think your wisdom is having, a good impact. But
My wife says it's madness, not wisdom.
well, your madness is having some impact. But on the thermal side, how are people supposed to, instead of just pointing the finger and saying, well, they can't just plug in this U factor and say we have 30% glazing and the window assembly is a 0.28 U factor, so just plug that in and what's your opaque value and there's our envelope performance. Now, obviously, it's very incomplete. But everything we started this podcast with in speaking about interface conditions and receptors and flanged profiles and the trim that comes out or your slide and anchor or your end caps on your receptor components, all these little ancillary accessories that are probably driving more of the overall thermal performance than the actual window itself.
The end
How
ends
is
on a
all that
receptor.
accounted for?
The end ends on a receptor are not driving the thermal performance,
I'm
except
laughing
in
because
2D. In 2D modeling, which is static, it sets an inside and outside boundary condition, and it assumes that 24/7, 365. So
fine. I was saying that one.
no,
to piss
but
you
we
off,
see
but
it. We see it. We see people are stressing over stick pins on insulation, wondering what that thermal bridge that's surrounded on everything but the outside point of the pin sticking out and thinking that this is a terrible thermal bridge. Sure, when you model it in software that's 35 years old, only works in 2D, again, is static, not dynamic, it looks terrible. But I always go back to money. I don't buy my energy in U value or R value. I buy my energy in BTUs and kilowatt hours. Every month I get a bill, and that's what I see on my bill. And I pay X dollars for X BTUs or per BTU. We need to separate compliance from performance. And this is one of the early podcasts we did together. I talked about compliance versus performance. Lots of my LinkedIn posts in the old days were about that. And I think I have to start talking about it again. I am not anti-U factor and R value in the code. And having a prescriptive method for designing buildings by utilizing those terms. I am 100% in favor of having prescriptive methods for meeting the building code. You want to know why? From empirical data, we know that if you use this U factor window, the building is good. The building is good. I can't tell you how much energy you're going to use every year. I know compared to a building that was built 10 years before, we have a 3 times better improvement or a 300% improvement in the overall efficiency of the building. Am I trying to figure out hourly weather data, wind, outside temperatures? No, I'm not doing any of that. I'm just saying I know that if I build a code compliant building in 2026, the owner's not going to spend enormous. They may. I mean, the building size obviously dictates how much you spend on your energy, but the owner will spend an appropriate amount of money purchasing their energy as long as they're responsible and the tenants don't leave the windows open in January. I can't do anything about that. Neither can the building code. We can only do so much by codification. But if we build a code building today, not passive house, not LEED, not net zero, a code building, really code building, meaning continuous air barrier, continuous insulation, good U factor windows, good R value insulation, you're building a really good building. But it needs to be built that way, which means someone who knows what they're looking at needs to look at just about every inch of air barrier on that building, all the interfaces between the opaque air barrier system, which is also the water barrier system, and the interfaces around windows and doors, penetrations through the wall, tie-ins to the roofing, tie-ins to the below grade. All that stuff comes together to make your building air barrier with a large A and a large B. The air barrier material that you roll on, peel and stick on, whatever, spray on, that's air barrier with a small a and a small b. That's the product. The continuous air barrier of that building is all those systems and products performing well together. It's the number one thing that will make your building perform well. The number two thing is continuous insulation. That doesn't mean every square inch of the building has to have all the insulation or even have insulation. But the majority of the window has to have insulation, and the insulation has to continue from opaque areas, below grade areas, to penetrations. Obviously, a window is not as high performing as 6 inches of mineral wool, right? It's just not going to happen until we really get to high performance framing and vacuum insulating glass. But today, we need to accept that those ratios and those minimum U values or U factors are there for a reason, because we know if you're below this much clear area on your building and you use this U value window, the space is going to be comfortable. You're not going to be sucking down kilowatt hours that you shouldn't be just to keep the interior conditions. It's all about loads, right? I can insulate the hell out of a building. I can put the best triple quad glazed windows in the building. If I have crazy loads inside, it's still going to be an energy hog. But for normal buildings, if the energy code says for residential buildings of this type, we need this, believe me, that didn't come from nothing. That came from people who were around for a long time, who looked at the empirical evolution of these buildings and where we got to and what worked and what didn't. And, there's more complicated stuff. Joe Stiebrick likes to say we used to build our buildings out of rocks and stones, and he's right. And rocks and stones, concrete, everyone's talking about concrete and embodied carbon. Concrete's a great material. If it's well done, it lasts multiple 20 generations, not 2, right? It also, I tell everybody, it's a sponge. It has terrible U value, no R value. It's like R point whatever. It has shit R value, but it's a sponge. It soaks up. If you put a sponge in your sink under the faucet and you have your faucet dripping, drip, 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 how many drips is it going to take before that sponge gets saturated and starts to leak out of the other side? Lots of drips, right? Stone, brick, concrete are a sponge. It absorbs energy, whether it's absorbing the interior hot air when on a cold day or the exterior solar heat gain hitting that or the exterior hot air. It's absorbing that the whole time there's a temperature differential. It wants to move because it has very high conductivity. It's got a very high U value. It wants to move from hot to cold, but it absorbs it. It builds up in there before it gets to the other side. And what usually happens before that happens? The weather shifts. Day becomes night, night becomes day, and all of a sudden. But that's a whole other very, very complicated design philosophy that people knew intrinsically in the old days how to do it. We built mass walls for a reason, and I'm not advocating going back to mass stone or masonry walls, but it worked in the old days without complicated, intelligent barriers, without, tons of insulation. We just have to go back to basic first principle stuff. Heat moves from hot to cold. Moisture also usually moves that direction. And we have to just learn the basics. I mentioned Joe Stiebrick, spelled LSTI. Everybody should go on YouTube and look at the stuff he's done. Some of it's old and shitty quality video, but what you can learn from guys like him and John Straub and lots of other people who came way before me and taught me stuff. We should all be learning from those guys. You learn first principles, you realize some of this minute analysis is not necessary. Joe will be the first one to tell you he never uses Wolfie, right? There's a reason. You don't need to. You don't need to. There's very few conditions when you need to model things at that level. Sorry, I know I got off topic there. I know you're shocked.
It's been a while, and we've been waiting for it. A little bit of the madness. So we're gonna bring a little bit more performance over compliance theme back to this podcast. Eliot, thanks for joining, and we'll have you back here soon.
You got it. Thanks. Hey, thanks for having me.